problems. So in our warm-up, to get us started, from yesterday, the effective interest rate is actually higher than the interest rate. So remember, we saw that if we have interest accruing more than once a year, we actually end up with a higher interest rate by the end of the year. So the question is, number 2, would you rather have compound interest semi-annually or monthly? And hopefully after yesterday, you would say monthly. The more times that you have interest compounded, the more money you're going to get. So essentially, we're going to get more benefit for us if we can have interest happen more than once a year. So today, as we look below the warm-up, it says that money is not the only real-world phenomenon that can be modeled with exponential functions. So some other ways we can model these, we can use population, which we saw a little bit last year, bacteria, we saw that a little bit last year, radioactive substances, electricity, temperature. So there's lots of different ways that we can model real world situations and have exponential functions be their form. So we're going to look at a couple of different types of problems, and we're going to start with what's called exponential growth or decay, because sometimes things can grow or they can decay. And so this is referred to as uninhibited. Nothing is acting upon this. So growth and decay. So we're going to still see exponential functions, just maybe written a little bit different. So I'm going to write some function notation here. A of t, so we're a function denoting time, is equal to a sub 0 and times e, so we saw that in the last video, to the kt. So a couple new things about this equation, but one really quick, k needs to be greater than 0. We want that value to be greater than 0, else we just end up with e to the first power, because timesing by 0 changes that exponent to 0. So a of t, similar to the last two videos, a is going to refer to that final amount. It just may not always be money now. And a sub 0 is that initial amount. So again, because it's not money, it's not going to be referred to as principal. K is what is called a growth constant. So K is our growth constant. And time is still t. So let's look at example 1 and see how we can use this formula here. So it says a colony of bacteria that grows according to the law of uninhibited growth is modeled by the functions. So we're going to give you these functions today. So it's in that form that we wrote above, where A is measured in grams, so there's our units, and T, time, is measured in days. So problem A says to determine the initial amount of bacteria. So as we've reviewed in an exponential function, that initial amount must come before its rate. So in this case, that initial amount is at A sub 0. So in this equation, our A sub 0 is 100, and this is in grams, it says. So we have initial amount of 100 grams. And what is the growth constant of this bacteria? So our growth constant is K, and K is in the exponent next to our time. So our growth constant here this time, that K value, is 0.045. C, the population after 7 days, we're going to have to calculate because there's our time. So into our equation they gave us, let's calculate A of 7, because we're looking for a time of 7 days. So I've got 100, that initial amount, times e to the 0.045, but we're multiplying that by 7 days. So to my calculator, I'm going to plug this in, 100 times e, on that left side down near our on button, to the 0.045, but we're multiplying that by 7 days. So in this case, it looks like we're going to have about 137 point, I'm going to keep doing 2 decimal places, 0.03, 0.03, and this would be days. What is the population, excuse me. So we're going to have about 137.03. So this is about how big our population is going to be after 7 days. Part D, how long is it going to take for the population to reach 140 grams? Now, as we saw in the last video, because time is an exponent, we don't know how to solve for time this year without using a system. So I'm going to take that original equation. I'm going to think about using it down here in D. That's my first equation. But my second equation, I want to know when is it going to get to 140. So if I graph that horizontal line, y equals 140, and see where it intersects my equation, I'll find out how many days it's going to take. So I'm going to go to my y equals, and if you've got something in there, go ahead and clear it out. And let's put in that original function, 100e, and it's to the 0.04. Again, we're going to use x because time is on that x-axis as we're graphing it. And my second equation is going to be 140. So remember, before I press graph, I want to go into my window and change things. So this time my intercept is a little bit smaller. I just need to be able to get to 140. So maybe I make it easy and call it like 200. But I probably don't want a 100 scale like I had for the last problem. Maybe I want it to go, I don't know, by 25s or 50s. I'm going to do 50s. I don't know what I want my X max to be. Originally, the calculator would set this to be 10. So maybe I want to see what 10 does if I need to change that at all. So I'm going to go ahead and press graph and see what happens. So there's a piece of my exponential and there's my horizontal. So I didn't need it to be any bigger than 10. So let's find that intersection. Second trace, number 5. Enter, enter, enter. Let's see, when it's 140, it's going to take about 7.48 days. So I'm going to go back and write here, how long is it going to take? It's going to take about 7.48 days, so almost 7.5 days to reach that 140 grams. So, yeah, we weren't looking for money on this one. We were looking for a day, a population. We're looking for grams. So again, an example of when we're using an exponential function, this growth, it just didn't involve money. Let's try example 2. A dinosaur skeleton was found in Vernal, Utah. Scientists use the equation. So again, we've got this nice equation in our form where A is measured in kilograms. So there's our units. And T is measured this time in years to determine the amount of carbon remaining in the dinosaur. This in turn helps to determine the age, which is something maybe you've learned about in science before. This is our carbon dating. So part A, determine the initial amount of carbon in the dinosaur bone. So according to our equation we're given, that initial amount is 1100. And we want to make sure we put our units. This would be in kilograms. So about 1100 kilograms of carbon were in these dinosaur bones originally. What is the growth constants? Well, this time we're decaying. We're decreasing, as it says it's negative. This is losing carbon as time goes on. So our constant this time is a negative value. So we want to make sure we get that whole decimal in there. See how much is left after 5,600 years. So dinosaurs died. How much carbon is left in there after 5,600 years? So I'm looking for a value of my function of 5,600 years. So I'm going to plug into my equation a time of 5,600. So this is definitely decreasing as time is going on. So I'm going to go back to my calculator and I'm going to type this in. So I've got 1100 times E to the negative 0.000124. And we're multiplying that by 5,600 years. Enter. So according to my calculator here, as long as I've typed everything in right, how much is left looks like is about 549.31 kilograms of carbon would be left in these dinosaur bones. So if we started with 1100, we've definitely decreased probably about half almost, it looks like. So problem D, how long will it take for the carbon to reach 900? So we know 5,600 years took us to 549. How long would it take just to get to 900? So again, this is a system of equations. So I'm going to take this equation that I was given, and I'm going to use it down here on part D to go along with that 900. So using that system of equations, we'll figure out when they intersect. So back to my y equals, let's see, this time I have 1100. Guess you could clear this out and start over. 1100 e to the negative 0.000124 to the, or I don't need a parenthesis, excuse me, I'll just put x. And we're going to do this, we're hoping to find for 900 years how much is left. So again, I'm thinking about my window. I need to make sure I'm starting at least at 1100, because remember, this is decreasing. So it's starting at 1100 and it's coming down to 900. So maybe I want to go up to like 1200 in my window. So this is going to change my max to quite a big max. Maybe I want to count by 50s. Maybe I want to change it. I think I'm going to change mine to hundreds. Technically, this could, I could change this, but I'm just going to keep that as 0. And maybe I just keep it as 10 for right now in my X max. I don't know how many years it's going to take. So maybe I start with 10 and see what happens. Or maybe I think, well, it took 5,600 years to get to 549 kilograms. So 10's maybe not enough. Maybe I want to go to like 4,000 or something, make that a little easier on myself, which would mean I don't want to scale by ones. Maybe I do hundreds again, just to see what happens. So this time when I press graph, I should see that decreasing function. Oh, and there's my line. Let's calculate that intersection. Second trace, number 5. Enter, enter, enter. So let's see, when we have 900 kilograms, it looks like it's going to take us 1,618.31 years. So not as much as I maybe thought it was going to be. 1,618.31 years. Let's turn it to the back side and see what else we can look at here. We're going to look at a little bit different form of our function. Let's start by writing here. We have a sub t, again, writing it in our function notation of time, our function of time. Still thinking about a sub 0, that initial amount, but we can also have it a b to the t. Or kind of in other words, we're thinking of our a sub 0, and we're breaking apart that rate, similar to we saw in our last video, of 1 plus r. So if it's plus r, we know that we're increasing. So to find that b value, we're looking for 1 plus r. So a sub 0 is still the initial amount, but b is going to be replaced with that 1 plus r, which is just that growth factor. How much are we increasing by? So again, there's some restrictions. We want b to be greater than 0, and we don't want it to be equal to 1, because 1 to any exponent is just going to be 1. So this would give us an exponential growth. If our r value was less than 0, it would give us a decay. So we can have a decay or a growth. So let's look at example 3. Michael bought a new laptop for $1,800 last year. A month after he purchased it, the price dropped to $1,665. So we want to identify in part A the growth rate, that b value, that rate. So let's take, and we kind of learned this in a 7th grade math, where we take that new value and compare it to the old. So I'm going to go to my calculator and take 1665 divided by 1800. And that's going to give us 0.925. Well, this is our B. So our B value, which we can replace with 1 plus R and help us solve specifically for our rate. So if we subtract 1, so 0.95, if we subtract 1, we end up with a negative, which I'm not shocked that it's a negative because we are decreasing. So we are decreasing, and if we change this to a percent, we'd have negative 0.75%. So this laptop went from $1,800 last year and is now $1,665, which means it's gone down 7.5%. Part B wants us to write an equation to model the value of this computer. So I'm going to follow what I've got up here in my exponential function. I'm going to make this a function of time. So A of t, I know my initial value of my computer is $1,800. I know my total B is 0.925. And we're doing this for an amount of years. So T is time. Part C wants us to do what is the value of the computer after 9 months. So I'm going to plug in for time 9 months here. So 1,800 times 0.925 for 9 months. So into my calculator, 1,800 times that quantity of 0.925, and we're going to do this for 9 months. So after 9 months of owning this computer, it now has a value of $892.38. We'd round that 7 up. Part D, when would the value of the computer be $500? So how long is it going to take? How many months until this is only worth $500? So again, we have a system of equations. So we're going to take that equation that we already wrote and we're going to put it with the 500. When is this going to be 500? So back to my calculator and go to my y equals, and I'm putting in my 1,800 and in parentheses 0.925 to the, again, we're going to use x instead of t, and we want to know for 500. So this is decreasing. So again, my higher point, 1,800, I would like that to be there. And I know that it needs to intersect at 500. So into my window, I'm going to set my max. Maybe I set it for 2,000. That's a little bit higher than my, whoops, that's my scale. I'm going to set it a little bit higher. And maybe I'll scale it still by 100. My X's, my time, I don't definitely want it to be 4,000. Maybe I take it back to 10 and see if that's big enough, which means I want to change my scale back to a 1. So let's see if this will work for us. So I should see my decreasing exponential. So there it is. And then I'm looking for that horizontal, which dang it, is not going to intersect in 10 years. So I need to go back and change my window. Maybe I'll change it to 20. See if that finds my intersection. So again, there's my exponential function. Oh, and there, that will work. So not quite 20 years, so getting closer though. Second trace, number 5, enter, enter, enter. So let's see, to have $500, or my computer being worth $500 is going to take me about 16.43 months. So about 16 and a half months, my computer, my laptop that was bought is only going to be worth about $500. So sometimes we lose money on things, and that's okay. It happens in a lot of things. Okay, let's look at one more example. Example 4. The population of West Jordan was just a little over 100,000, 106,863 people in 2011. The population is growing at a rate of 5% per year. So I know that I'm looking to change that for sure if I was to be calculating with that. A wants us to write an equation to model the population growth. So we are increasing here. So I'm going to do a function of time again. Our initial population, 106,863. Now I'm increasing this by 0.05. So I could just write this as 1.05. So I'm going to erase that. 1.05 to the t. We're looking for that time. And B says, if this trend continues, what will the population be in 2020? So we're looking for a time of 2020. Now, I'm going to think about this a little bit different because it told me 2011. So 2020 is 9 years after 2011. So I'm really going to be thinking of this as 9 years later. So my initial population, I have how much it's growing by. So I'm looking for this 9 years later. So into my calculator, 106,863 times 1.05 to the 9 year. Oh, so it's grown a little bit. Yeah, 165,000 type people. So let's see, we'd end up with 165,779. And people aren't really in decimals, so I'm going to leave this as a whole number. So according to this, if it continues at that trend, in 2020, we'd end up with 165,779 people. And the census was taken in 2020, so that's something I guess we could check. So problem C, how long before the population grows to 125,000? So we know it takes 9 years to get to about 165,000. So how long until it's 125? So again, I'm going to use a system. I'm going to take that original function I made and see when it's going to intersect 125,000. So to my y equals, I'm going to put in my equation 106,863. That's a pretty big number. In parentheses, 1.05 to the x. And I need to put my 125,000 as my horizontal line. Now, these are some pretty big numbers. So this is increasing. So I want to make sure that I'm have my 106,000 in there and it's increasing to 125. So in my window, my Y max, I don't know, maybe we want to have it closer to like 150, 130, 140, something that's a little bit bigger. I think I'm going to do 130,000. Be just a little bit bigger than that line. And I want to probably count by some pretty big numbers. Maybe I want to count by thousands. You could even count by maybe 10,000. I think I'm going to do it by 10,000, see what that does. My max, well, I knew that it took 9 years to get to 165. So maybe the max being at 10 and just counting by ones is going to be enough. Let's see what this looks like when we graph it. Oh, so it's definitely increasing. It's thinking. Sometimes we give our calculator some pretty big numbers, and it may take a second to think about it. I feel like I should have seen that. Let me go check my window, make sure I didn't miss something. So I've got 130,000, my Y max. So I want that to be 125. I counted by 10,000s. Oh, let me try graphing that again. I thought that should work. Maybe it's thinking a little bit longer. I'm not sure why that's not coming up. Got my scale and my Y max. Double check my equations. Oh, look, I have an extra 0 on my second equation. That should, too many zeros. 125,000. Let me just clear that. 125,000. Okay, now let's graph. There we go. So right at the top, I didn't give myself too much extra room, but I should still be able to do my intersect and enter through. And let's see, to get 125,000 people, it looks like it's going to take me a little over 3 years. So maybe I'll just say that the time, because we usually calculate, is going to be about 3 years. So how long before the population? It's going to be 3 years. Or if you wanted to kind of give an exact year, kind of like the problem did was 2011, maybe you want to just count 3 more years. So I would take either of these as a solution, put an or between those. It would be 3 years after that 2011 or 2014. All right, go ahead and self-assess. How do you feel about exponential growth and decay type problems? And good luck on your assignment.